The translation is
Oi.
all good, so we can start now. Thank you
Bye.
very much.
Excellent. Well, I hope we have everyone on board here. And I'd just like to say welcome to the third webinar on addressing water management challenges through decision scaling and adaptation pathways. And we're excited to have everyone here. We've had talks on Zambia and on Chile, on Thailand and Mexico. And today we have some of the classic speakers, shall we say, in decision scaling and bottom-up water resources management. And so we'll be hearing from Casey Brown of the University of Massachusetts and Alexis Dufour of San Francisco Public Utilities Commission. And then we'll be hearing also from Andrew Warren of the climate group at Deltaris. And we'll have some time at the end for discussion. We will also, for the first time today, have translation to French. And that should be at the bottom of your screen. I don't see it at the bottom of mine, but hopefully it's at the bottom of yours. So bonjour à tous for that. And if you have any questions, we'll be using the chat room, maybe the Q&A room. Alex can help us decide on that, but you can be putting your questions in along the way for the speakers. I'd like to say one more thing before we get going, which is that there's an upcoming course, UNESCO course on climate risk-informed decision analysis, or CRIDA. And this is at Open Learning, all one word, openlearning.UNESCO.org. It's opening up on the 1st, that is, I think, Sunday, and it's semi-self-paced. There's a limit of time, but it's basically a self-paced course. It's the first one. It's the absolute first course for UNESCO's new open learning platform. So we're very excited about that. So with that, can we move to the next slide then? Shall we introduce the speakers then? I guess the answer is yes on that.
Excellent.
Yes.
Okay. So the first talk then is from Casey Brown and Alexis Dufour. Casey Brown has his background is actually from Harvard, where he studied with Peter Rogers of the famous Harvard Water Project. And so unlike most people who develop their interest in water management along the way later, he has the background right from the beginning for that. And that made him one of the founding fathers of decision scaling and eventually CRIDA and decision tree. And along with him, in some sort of coordinated fashion, is Alexis Dufour, who is a water resources engineer at San Francisco Public Utilities Commission. And again, like any number of engineers who thought engineering was fun, but realized that the real action was in how you communicate the engineering problems and integrate them with the social sciences and the decision making. So with that, I'll turn it over to Casey and Alexis.
Great, thanks, Will. Thanks for that kind introduction. And that's exactly right. Myself and Alexi will share this presentation. I'll kick it off, and then Alexi's going to get into the details of our most recent and ongoing work with the San Francisco Public Utilities Commission. I am going to share some slides with you. And I'll pause to make sure that this is sharing effectively. Everyone see that okay? Thumbs
Yes, we
up.
do.
Okay, great. Thank you. So thanks again, Will. It was a great introduction. My name's Casey Brown. I'm a professor of water resources engineering at the University of Massachusetts. Again, joined by Alexis Dufour from SFPUC, the water enterprise there. I'm going to talk about climate-informed adaptation through decision scaling. This is what we're working on right now. And I want to start off with this general, to me, really the crux of the issue is it's crux of adaptation issues. It's a crux of understanding climate risks. And that is, how do we use climate information for decisions? And frankly, it goes beyond even climate information. What it's really about is how do we use predictions of the future that potentially have some information value, but are uncertain? How do we use those to make better decisions? I think this is something that we struggle with. Those of us who want to use the best available science that inevitably comes with uncertainties, how do we use that information for decisions is a great challenge that we all face. So I like to think of it in terms of an axis of uncertainty as I'm presenting here. On the right side is where we would like to be, where we have well-characterized probabilities to assign to our uncertainties. And this is places where the science is well understood, and we have huge samples to help us characterize probabilities. And in these cases, then a predict then act framework works very well. On the other end of the spectrum is to the left, where we describe this as deep uncertainty. And essentially, we can't assign any probabilities to the future. It's too uncertain. We can use things like scenario analysis, or there's the approach called robust decision making. They've been very good at helping us to characterize, using sensitivity analysis, characterize how these uncertainties might face us, what our vulnerabilities might be, and through essentially sensitivity analysis or through the use of scenarios. And we avoid assigning probabilities at all. The key is, I think, that neither of these situations really applies for climate science or for many different kinds of scientific predictions. They actually do have information value, maybe not sufficient to assign uncertainties, but certainly to inform decisions. And so the method of decision scaling that we developed is to address this part of the axis of uncertainty that's right in the middle, where we have predictions, they can have value. How do we make the most use of that information and that value? The key is how you use those predictions. How do you use climate projections, but how do you use scientific predictions in general? And when it comes to climate change, the key question is, how do we use climate projections? Now, on the left, I show sort of a cartoon of how projections have typically been used. They've been used to make predictions of the future, to really try to fit back into that predict then act framework that is where we're used to working, frankly, where we typically look to science to reduce uncertainty for us to make our decisions a little bit easier. And so climate change was the same way. We looked to the best available science, we came up with projections. These projections we were hoping would reduce the kinds of uncertainties we would have to consider. And the problem is that much of the use of climate projections came from a framework and a mindset of motivating action on mitigation. So let's talk about the worst case scenario, because the worst case scenario is what we're worried about when it comes to mitigating climate change. In other words, reducing our greenhouse gas emissions. But when you're a practical decision maker in the water space, you have to think about more than just the worst case scenarios, because there's huge costs to taking action that might not be needed. So you have to consider the whole possible range of outcomes. And that's really where the method of decision scaling came from, trying to inform these practical decisions that are all about not mitigation, but in fact, adaptation. And so on the right, I have a cartoon of the approach that we developed, which focuses on first the vulnerability domain. understanding where we're vulnerable. And this takes the best of the robust decision-making framework, where we use sensitivity analysis in a multidimensional framework to understand the individual stressors or the stressors working in combinations that cause a system to be vulnerable, and allow us to identify the actual levels at which those uncertainties can cause vulnerabilities. And we call this an ex post scenario analysis, ex post identification of uncertainties. Our key innovation is then to take those uncertainties and those vulnerabilities that have been identified and use those as a lens to view the climate science. And so now that we understand what our vulnerabilities are, we can look to the climate science to extract from that what it says about the level of concern we should have for those vulnerabilities. That's really the essence of it. And it's just, again, it's designed really about answering the kinds of questions that need to be answered if we're going to take action on adapting to climate change. And so those begin with, really, is my system vulnerable? Am I vulnerable to climate change? What kind of climate changes are problematic for my system? And then in response to that, what actions should we take to prepare for climate change? And the methodology is designed to answer these two questions, and we'll walk through that today. We developed these steps to implement this general concept of decision scaling. It begins with identifying what the key uncertainties are. These are really the framing of the analysis through discussion with stakeholders in the place that we're working. We surface what are the stressors or drivers of the future that need to be considered as we think about adaptation. We know that it's not just climate. In the places that we work, there are other factors. From a water perspective, it can be demand, it can be regulatory change. All of these have to be considered within the context of considering the future and the choices that we make relative to the future. In some ways, this is tricky, right? How do you know what the key uncertainties are until after you've done the analysis? And this is certainly something that we struggle with all the time. We realize that there are unknowns out there that'll also affect our decision. In some ways, that's why I think of what we're doing is really building more resilient projects. We can't account for every uncertainty that are out there, but we certainly want to understand what the vulnerabilities of the system are to the uncertainties that we do know about, and make the system more resilient in response to those. So we understand vulnerabilities after identifying these uncertainties by using a stress test. And a stress test can be either a multi-dimensional sensitivity analysis, where we perturb the system with all the possible changes in these drivers or in these external factors that we can think of and that we can model. And I'll tell you, we can model many, but in some cases, actually, a narrative approach works as well. And so there are some factors or drivers that are out there that need to be described more as a narrative, as a scenario. And we can use those individually or in combination with the more mathematical sensitivity analysis. We use those to understand and identify the vulnerabilities of the system. We use that vulnerability understanding to go to the climate science and to extract, again, from it, what does it say about the vulnerabilities that our system has? And then we can repeat the whole process for all the proposed adaptations to evaluate the vulnerabilities and the robustness of different adaptations. And so we'll illustrate that today with an example. First, I want to give you a little bit on the modeling process. Now, I know some of you will say, all right, I'm not interested in models. Please don't talk about models. And for the most part, I won't. But I do want you to pay attention to one part of this. It begins with a definition of the system, and in many cases, we will either create a new model of the system or we'll work with someone's existing model. Once we have that and we have the data that describes the external factors needed to test the system, we take this model and the data stored on the cloud so we can run many thousands of scenarios that fully characterize how this system responds to all these different changing factors. Then we can use machine learning algorithms to extract from that big database what are the key vulnerabilities that we should be concerned about. We can do the same thing for different proposed adaptations. And then the key part is, all right, now we have this information. We need to communicate it to decision makers in a way that they can understand the results. And so we spend a lot of time thinking about that as well. we'll show you some today. Hopefully they will communicate our results clearly to you. But I want to say, this is the key part, even for those of you not interested in models, I don't think we can do this work. And to a large extent, I'm concerned we cannot adapt to climate change without creating models of our systems. Some people call them digital twins. I think this is essential. I think we have to be able to characterize how our system is going to, how our various systems are going to respond in the future. And there's big questions. What about lack of data? What about water systems that don't have the capacity, technical capacity, financial capacity to build and model their system? These are important questions that I think we have to figure out. It's a preview or a lead-in, a prelude to a work that, a new project that we're kicking off, funded by the National Science Foundation with an all-star cast, I'll say, to try to develop machine learning algorithms and use AI to create systems for the water systems, frankly, that don't have the capacity to create their own models. How can you create models that can work for all systems? And we're trying to develop AI methodologies that we can host on the cloud. You plug in just a little bit of information about your system that is easy to do, and then we can do the analysis for you on the cloud. And in doing so, create local estimates of water-related risk at any location, even for small systems. Okay, that's a little advertisement. We're just kicking this off. And if anyone's interested in this, please reach out and contact me. I'd love to talk about it more. Okay, what are the results of these kinds of analysis? What we'd like to achieve in anywhere we work is, again, understanding the conditions that make the system vulnerable, being able to estimate a level of concern associated with those vulnerabilities, and to be able to assess the ability of proposed alternatives and proposed adaptations to reduce vulnerability. Okay, there I'd like to hand it off to Alexi, who's going to walk through this recent and current example that we are working on right now with San Francisco Public Utility Commission.
Thank you, Casey. We can hear me okay?
Yep.
Yeah, okay. Yeah, thank you, Casey. Thank you to UNESCO to allow me to present on this project. At San Francisco Public Utilities Commission in the water enterprise, we supply water to about 2.6 million people in the San Francisco Bay Area. And a couple years ago now, we've been trying to work towards moving away from our traditional planning method of predict and act towards a bottom-up, vulnerability-based planning approach. And we've been working with Dr. Casey Brown. Next slide. So the way that we started this effort was to assemble a group of decision makers within our agency and division managers and general managers and say, okay, what are the important sources of vulnerability according to you? And so this matrix shows these sources of vulnerability both depending on their importance as well as their uncertainty. Now this list is vast, and what it really shows is that addressing a single issue such as climate change for water supply planning is not enough. We need to address these other sources of vulnerabilities so that decision makers have a more holistic picture of the decision context. Next slide. So for us, we first limited to some of these sources of vulnerability. Financial health is extremely important. Infrastructures, drinking water, water demand, environmental regulation, which mainly means in-stream flow requirements below dams. We are a big dam owner in California, as well as climate change. Now, to address these different sources of vulnerability, we took two approaches. One is narrative or smart thinking, and say, working with stakeholders within the agency, what are plausible, interesting in-stream flow requirements to look at, similar to infrastructure failures? What are interesting failures of infrastructure in our system that we should be looking at? And then there's another approach, which is the stress testing, where we go through a modeling exercise of multiple scenarios of potential change. Next slide. So the way that we structure this stress test is initially with a weather generator. And the purpose of the weather generator is that we're not only bound to our historical sequences, which we've been using in the past for planning, but now we can actually explore other sequences of weather that allows us to represent the natural variability of climate. And so for this project, we have 9 realization of 50 years. So it's 450 years of data. Then we feed this information into a hydrologic model. But with this weather generator, we then have the ability to perturb the climate, so changes in temperature, changes in precipitation, to feed into the hydrologic model. So we have 6 temperature scenarios and 17 precipitation changes. And they represent a wide range of plausible changes within our region based on GCMs. We feed into a hydrologic model, and hydrologic model is key. If we don't have a calibrated hydrologic model, we don't have anything for our study. The output of this hydrologic model is now 9 realization times 6 temperature times 17 flow realization. And all these realizations now are fed into a reservoir system model that simulates how the water in our system moves between the different reservoirs and feeds into the different treatment plants to the demand nodes. We add to here 9 scenarios of change in demand. There's large uncertainty in demand projections, so we don't want to limit to a single demand, but we actually want to explore a wide range of plausible demands based on our econometric demand model. Then this informs the calculation of performance metrics, and the performance metrics have been decided working with analysts and decision makers, and are representative of some objectives that we have within the agency. So I'll just walk you through a single example of a metric. So it's the reliability of water deliveries. And that's basically means the frequency of year the system delivers our full demand, and we have no rationing that's applied. So in California, we are prone to droughts, and we have a single wet season between October to April. And by the end of the snowmelt in the high Sierra Nevada, which happens around July 1st, we basically have a sense if we are going to have enough water or not. And that's when we declare rationing. So in general, when we ration in California, we ration for an entire year. So frequency of years, the system, so our critical threshold here, our target is to be at 90%, which means that on average, we would ration 1 year out of 10. Next slide. So this is a representation of this metrics this metric on the y-axis, and it's plotted against the change in rainfall. That's the main driver for this metric. It's not very sensitive to temperature increase. And so we see that this blue line is for our demand baseline, so current demand. And we see that we're currently fine. We're exceeding our target. At the 0 change in precipitation, we're above 90%. But as soon as we're going to have precipitation potentially changing and reducing, we will have eventually crossed this line and will be vulnerable if precipitation decreases by more than 20%. Next slide. So that means that we can identify here the portion of this graph where we are vulnerable in red and we're performing acceptably in green. So the next step now that we have identified these 2 areas is to actually evaluate our level of concern. And to do so, we can use GCMs like Casey mentioned, but we can also use expert elicitation. And so here at SFPUC, we decided to do both. So we had a climate information workshop where we assembled a panel of climate scientists with expertise on climate on the West Coast of the United States, to try to develop an agreement on the range and, if we can, the probability in quote, of changes in temperature and precipitation. What is the most likely scenarios for our region? Next slide. Casey, next slide.
Yeah, I clicked. It's coming, I guess.
Oh, I don't see it. Casey, do you see it?
Yes, it's up on my screen. It's maybe a lot of data on this slide. Is that why it's slow?
Well, I don't see it, so I guess that, Casey, you can go ahead and continue your presentation, since it would be difficult to talk without seeing the slide.
Yeah, Alex, I'm curious, do you see a slide that says reduce or increase uncertainty?
Yes, I think Alexi's video is lagging a bit, so he's frozen. So,
okay.
So I think we can see it just fine.
Okay, great, thanks. Good, right. So it goes back to this question of how to use climate projections, and there's often the idea that if you use climate projections, then you've accounted for all the climates that you might see in the future. We're concerned that that might not be the case, and this elicitation session with the climate experts really validated our concern. So what I'm showing here is the projections from GCM, which you're used to working to. They're shown here as dots. And then the X's are the range of possible changes that the climate experts communicated via this elicitation approach. And what's interesting is you can see the range of the X's is wider than the range of the projections, the dots. And that's shown down below as a histogram as well. So if you look at the histogram of the GCMs, that's the top row for precipitation change, you can see generally it ranges from, let's say, negative 18% change up to about a 25% or so change. Now look below that to the range that the experts said is possible. Minus 30% change in precipitation up to over plus 30%. That's what they see as the possible range of changes, which is a pretty big deal when we just said that San Francisco is vulnerable for a 20% reduction of precip or more. GCM say no problem. Experts say, well, you can't rule that out. So that was just an interesting way to bring another way of thinking about what uncertain climate looks like in the future in terms of the level of concern that you should have. And again, this is the idea that the models are great, but they don't capture all that we know about climate change just through understanding the physics, but also understanding some of the gaps and biases in the models. So this is an important and eye-opening approach to bringing more information in to our vulnerability analysis.
I think I'm back.
Okay, good. Yeah, take over.
So now if we then add these distribution of GCMs and this distribution of expert elicitation and plot against our metric, we see that we have one GCM that predicts less than 20%, and we have like 6 expert elicitation that predicts more than minus 20% of precipitation change in our region. Next slide. But that doesn't give us the full story, because this was a picture using our current baseline demand. Once we start adding different demand projections that are plausible within our planning horizon, the picture changes. And so the baseline demand here is for a value of 226 million gallons per day. A very important planning demand for us is the second one, 265 million gallons planning per day. And if you follow this curve, basically we will need a precipitation increase to actually stay above this threshold. Next click. And so now the actual zone of vulnerability versus a zone of acceptable performance is quite different. As I said, now we basically need a 5% increase in precipitation to be able to perform at this level of reliability. And this has become significantly more likely when we look at the different projections that are below. Casey, back to you.
Yeah, thanks. Thanks, Alexi. Sorry for jumping ahead there. Yeah, that's great. And so, and I'll just say that, as a result of this, what we think very clear understanding of what the vulnerability is. And the vulnerability understanding is derived separately from the projection of climate, which we think is very useful because there's no uncertainty about this top graph here in terms of how the system responds to changes in climate. Of course, there's some uncertainty, but it's modeling error and that kind of uncertainty. But we can compare it to now the uncertainty of the projections, the range of projections that show that the system is vulnerable in these scenarios. And look, a fair number of projections show that that future vulnerability is possible, or in some cases, with a fair degree of probability or likelihood, we would say, at least in a qualitative sense. And that was enough to convince the leadership of SFPUC that they have to start considering actions in response to climate change, which is what we're working on right now, just getting started on. So I wanted to share with you a different project where we applied this approach, and we've gone through essentially the whole process, including assessing adaptation options. And this is what we call designing for water resilience in the Valley of Mexico. And this picture really brings together how we accomplish these kinds of planning studies and vulnerability and adaptation studies, is that it's a combination of the computer code on the top, but probably equally and more important is the bringing together of stakeholders and the multiple viewpoints that really define what our objectives are in a study and that frame the analysis from the study as well. So this is a workshop from Mexico City. I'm going to skip right to the end. So these are evaluating different options. We're interested in the water supply for Mexico City. We did the analysis, the vulnerability assessment, made it clear again, they need to take action in response to climate change. So the question was, what are the actions they should take? How do they evaluate options in this uncertain future? And so we used the same sort of analysis and applied it to a large portfolio of possible interventions. We evaluated them in the typical sort of approach. How much water do you get, yield, for what cost? But in addition to that, we evaluated them in terms of their ability to recovery from shocks and their robustness to climate change. Those two things together we think are the essence of resilience. Each one of these circles represents a different portfolio of interventions measured in terms of cost, their yield, the water that they add, their recovery ability by color, and the robustness by size. Each circle is a portfolio of interventions, and we're not saying that there's an optimal answer here, that this gives you the optimal answer. It allows stakeholders and decision makers to understand the options better. They zoned in on the ones that they felt were reasonable cost and reasonable yield, and selected a particular portfolio of options that again gave them the water they needed at a reasonable cost, but also had high recovery characteristics and highly robust to climate change. And this led directly to an actual project from the World Bank that they're implementing, a $200 million intervention to improve the water supply from Cutzamala system to Mexico City. So I just want to wrap up here in terms of the results. Why do we do these studies? The goal is to give you an understanding of the conditions that make the system vulnerable. What are the climate change that make us vulnerable? This is a question we're answering. In addition, what is the level of concern associated with vulnerabilities? How much should we worry? Do we need to take action? If you do need to take action, what is the ability of proposed alternatives to reduce vulnerability? What action should we take? So that's it for us. I'm happy to answer questions at the end, and please reach out to me or Alexi and send emails if you want to discuss in more. My advance apologies for the translators for speaking pretty quickly at the end there.
Thank you, Casey and Alexi. May I just ask Claire-Marine if everything is going well with the translation? Or at least let us know if there are any issues that we can help with. So I'll assume that things are going well. We do have some questions. We've got maybe 8 minutes or so for these first couple of speakers. And the first one that we've got is Alexei showed a really interesting slide of sources of vulnerability. Unfortunately, there were a dozen or more. And how do you prioritize these concerns? How do you go about sorting through all of these different potential sources of vulnerability?
So that's a very good question. So first of all, we included climate change since it was the trigger for this study, even if it didn't rank the highest in the importance of sources of vulnerability. Then we also use demand, even if it didn't rank the highest, because we know it's a fundamental forcing for a water supply system. And so then we used in-stream flow requirements because we know that the state of California has a looming, there's an action that's actually been adopted and that can actually be transformative for our agency. So this illustrates that it's through conversations with decision makers and analysts to see which ones made the most sense to pick. Also, that some work had been done on natural hazards for us very recently, so we decided not to include it. So it's part of a conversation with the participants of the project.
Thank you. And a question that some of us had also for Alexei. Alexei, you're actually out there in the real world, not up in the upper echelons of academia. And as I recall, you're a member of the something called WUCA, the Water Utilities Climate Alliance. Can you tell us just a little about what that group is and what they do?
Absolutely. The Water Utility Climate Alliance is a group of water utilities in the United States, mainly all large water utilities. They're very large utilities, but across the country. And at the inception, the goal of WUCA was try to bridge the gap between the information on climate science that was coming and being published, for example, by the IPCC or the national assessments in the US, and actual practitioners in the field who are trying to adapt and to see how can we use the data that's provided. So that was the main mission of WUCA, as well as doing some lobbying for climate science and try to push and change the approaches and methodologies to include climate risk in planning for water utilities. I invite the participants to go to wucaonline.org and you will see our reports, various reports on decision making, on climate projections, recently more on what does climate change means to engineering design, or also what does climate change means to health of personnel in the field. So yeah, that's it.
Thank you, Alexei. Another question we've had is the reality of the world is that the politicos, the folks toward the tops of utilities and local water management agencies in general, they come, they go. When there's a simple model, you just kind of go and you explain the model all over. But I don't know if you or Casey has heard of cases where the leadership was very excited about this and then leadership changed and you found yourself back at square one.
Yeah, it happens.
Yeah.
I was going to say it happens. It's definitely a real factor. It's happened to me several times, I would say, in what I've learned from failures and successes, because there's definitely been failures where the plug just gets pulled, is to get a broad base for the work that you do. You know, if you're working with one person who's a real champion, but that person doesn't have a broad base within the organization, hasn't really communicated it and socialized what the benefits of the analysis are more broadly within the unit, within the organization, it can disappear. I think, you know, Alexi's done a wonderful job of that at San Francisco. We met with every different constituency, I would say, within SFPUC, brought people together who typically aren't in the same room talking about these sorts of issues. And I think, I mean, yeah, we have strong leadership throughout at the top as well, but there's a large constituency of people who are now looking forward to the results that go beyond just one person. In Mexico City, it was the same case. We worked so hard to really win the trust of the head of SACMEX, a water agency there, and at Canagua and Ocavam, these different organizations that dictate or have a lot of influence on water policy there. And the leadership changed. But we had met with so many people and worked with the private sector as well as the public sector that, again, there was just momentum and expectations within the community that went beyond a single person. So it's certainly a concern, but I think there's a way to address it. But I've certainly had failures as well.
Yeah, I would add that it's definitely a question about change management, and which is a whole field in itself. And so I keep saying very frequently, you know, if you want to go fast, you go alone. If you want to go far, you go together. And going together takes time, and you need to involve a large base of expertise within your organization, and making sure that everybody agrees. And we recently had a big setback on this project. You know, we had our final review panel, and suddenly a big decision was made that it was not acceptable, and we had to go back to recalibrate certain models. But all this to improve the product and making sure that we're all in agreement, and we'll all be supporting the approach.
Thanks, and I guess we'll wrap up the questions at this point. And if we have some time at the end, there are lots of other questions in mind by various folks. So if we can have I just want to thank the two of you, and please hang around in case there's some questions at the end.
Sure, thank you. Pleasure.
All right. So now the next talk. This is not just an American initiative. We spoke about how we've talked about projects in various countries along the way, and in Zambia and Chile and all over. And now we're going to have a chance to engage our partners at Deltares. And Deltares has worked very hard on something called adaptation pathways, which is it's kind of after the point of the progress of the process that the previous speakers were talking about, and we're at the point where we're trying to develop some robust solutions that are flexible solutions that can go in different directions. But Deltares is also big on serious gaming, the sustainable delta, for example. And so serious gaming is a topic that we're at the Corps of Engineers. We tried using that, and no one would fund our projects because it didn't sound serious enough. But with that, can we have the slides for the next talk up?
Thanks, Will. Maybe I'll just have a quick address to everyone first. So as Will introduced, my name's Andrew Warren. I work at Deltares here in the Netherlands. You may have picked up from my accent that I'm not Dutch. I am actually Australian, so just to give us a little bit more of an international flavour. and yeah, most of my work at Deltaris is in the field of adaptive planning and management, and looking at ways that we can apply adaptation pathways in planning processes. And it's interesting to hear Will mention serious games. I will mention them briefly in passing during my presentation, but we are actually working on a new game for the Corps of Engineers as we speak. So it may be that serious gaming as an approach does start to feature a little more heavily in some of this stuff, because it's a great tool to use to explore some of these issues and these concepts more fully. Anyway, I'll switch to my presentation now. Just make sure. So hopefully I get some sort of indication that we're on the right on the right screen from someone. You should just see a big blue Deltaris logo.
Looking good.
Looking good, great.
We do see it.
Okay, so just briefly, for those who are unaware, Deltaris, we're a research institute, independent research institute based in the Netherlands, but we're a key knowledge partner of the Dutch government. But we are independent, and most of the work that we do and the research that we conduct is to do with the surface and the subsurface, and how it relates to water management more generally. Apologies for the screaming child in the background if you can hear that. I won't dwell on this, but we also produce software products, but most of these are, of course, open source and freeware products for others to use and apply as they need. Today, as Will introduced, I'm going to be talking about adaptation pathways, or more completely, dynamic adaptive policy pathways, which is a complete policy analysis approach. So adaptation pathways is one part of the process, one part of the approach, but the approach itself is something much broader. And it's all related to a lot of what Casey and Alexi were talking about previously, where we're trying to confront these long-term uncertainties in our planning and trying to work out ways to plan for them, or to plan effectively in the face of these uncertainties, because we need to plan regardless. And why are we doing this? I won't dwell too much, but we know that there is change ahead in terms of the future. The climate and socioeconomic developments that we are facing are more or less increasing pressures on our water-related systems. For example, sea level rise and weather pattern change could be leading to greater storm surges. This picture is from Sydney in Australia from a couple of years ago, although I note that there was a similar event a couple of weeks ago where swimming pools are falling off properties located along the coastal areas. We could be experiencing greater floods due to increased precipitation events and these sorts of things. On the other side, we could be dealing with more water scarcity issues relating to reduced water availability as the climate changes, and increased droughts and dry spells. But then on the socioeconomic side, which both Casey and Alexi touched on, there's also forces at play that we cannot ignore. Population growth could be increasing competition for available resources, for example. Demand patterns could change. Populations could age in such a way that they increase pressure on public finances, and there could be an increasing urbanization such that leads to demand pattern changes in terms of, say, water supply in our water systems. But essentially what we know is that all these potential changes and potential futures that could eventuate, they're uncertain. We have no idea what direction they will take or the magnitude they will reach. And again, we saw that from the preceding presentation. But the key thing is that when we have to create these plans anyway. We know that there's going to be change in the future, but we still need to plan. So how do we do that? And the key thing is that it's about recognizing that the uncertainties exist and that we can incorporate them into our plans, and we do that through these principles of flexibility and robustness. Okay, so we don't want to ignore uncertainty. We don't want to plan for a single scenario, which may or may not eventuate, because if we ignore uncertainty, it means that we are limiting it. We can potentially limit our ability to take corrective action in the future. It could mean that we end up in situations that could have been avoided. It could mean that we miss chances and opportunities and lead to unsustainable plans. But essentially what we want is a plan that is robust across all potential futures, and that is flexible so that we can adapt it as the future unfolds. And that's essentially the crux of what Dynamic Adaptive Policy Pathways offers, or DAP. It's a systematic framework for adaptive planning that really that explicitly considers decision making in time. So it recognizes that adaptation is a path, that a plan or an adaptive plan is not static, and that there are many possible paths that we can take to achieve our objectives, and that we should be able to keep our options open and wait and see what new information comes to light before switching action. So it specifies short-term actions and thresholds beyond which additional actions are needed, and monitoring is an important part of the approach, where we formulate monitoring, we identify monitoring signals or parameters to monitor, to give an indication of the direction of change or the magnitude of change that we might be facing. And the approach, really, the benefit of the approach is that it helps focus on important questions of planning under uncertainty, such as what low regret actions can we take now that contribute to future goals? What are the robust and flexible strategies that are open to us? And so on and so forth. And the key thing that I would like to point out from this slide, or another key thing, is that it's particularly useful in situations where there is a higher potential for investment regret. And what I mean by that is, if we act in a particular direction, if we overinvest and we didn't need to, then that's a situation of regret. If we underinvested and didn't act because we were waiting to see what would happen, and then a calamitous event were to occur, then again, that's an opposite expression of regret. So the idea of pathways is to help identify where these situations of regret exist and help to navigate paths through that. The approach in a nutshell is expressed by this 7-step process. Now, it's presented in a stepwise fashion, but it's not a process that you can follow simply just one step after the other. It's iterative, it's messy. Sometimes you might be jumping from a later step back to an earlier step as new information comes to light, or new data is found, etc. But in essence, these are the steps that one must follow, and you'll see that it closely mirrors many of the steps that Casey presented earlier. Again, key is this initial description of the system. What are the objectives that you're trying to achieve, and what are the uncertainties that you're dealing with? And then it's an assessment of the vulnerability. And I might mention too, the potential opportunities. And we do that in a way that is very similar to what has been presented previously. But the idea is that we identify these thresholds, or these performance thresholds, vulnerability thresholds, against which we can say that our system is no longer performing acceptably. And that's what we refer to as an adaptation tipping point, or an ATP, or a threshold. An opportunity tipping point may be a condition at which certain actions may become feasible due to changing social pressures, due to economics, due to whatever uncertainties it may be that we're dealing with. Following from that assessment of vulnerabilities, we identify the actions that are open to us to address those, and then identify the timing of their tipping points or the new thresholds by using scenarios. Then we move on to this idea of developing adaptation pathways, and moving on to, and then following on from that, designing the adaptive plan, where we elaborate on the preferred pathway with short-term actions, long-term options, the signals we need to monitor. Perhaps there are some enabling actions that need to be taken, or contingency plans that need to be put in place, financing plans, implementation plans, so on and so forth. Okay, so just briefly on adaptation pathways, a little more detail on that. This is an adaptation pathways map. It's a theoretical adaptation pathways map. And what it shows is the different possible sequences of investment decisions that can be made through time, okay? And how they relate to the performance that we're interested in. So we have a horizontal axis. Let me turn on my pointer. We have a horizontal axis here, which indicates how the conditions are changing against our key performance metrics. So it's along this axis that we can see our system vulnerability, and can determine whether or not the various options available to us can address that vulnerability, and how much it can address that vulnerability. So it goes back to that idea of stress testing that Casey and Alexi were talking about earlier. Then we also have different scenario axes, which indicate the timing, or the various timings of those changes in conditions. So you can see here we have a low-end scenario in which conditions may change only this much in 100 years, but then in a high-end scenario, we expect to experience more change. And then within the rest of the map, you have your actions, and they indicate how much change your system can cope with were that action to be implemented. Okay, so in action A, we see that's a very effective action that can cope with a lot of change. Same with action D. Action B, on the other hand, can only cope with a little bit of change, right? And the vertical line here, or the terminal, is the representation of the adaptation threshold, or the adaptation tipping point. And essentially, creating pathways is the process of mapping out the thresholds for your system with each of the options implemented, and then constructing pathways if you were to take one decision and then move on to another decision and then move on to another decision. And you do that via the transfer stations. And what the pathways map illustrates is that, you know, perhaps you don't need to go for option A or option D initially, because you're not sure if you need an action that will be able to cope with that much change, because you don't know if that much change will actually eventuate. So perhaps you want to start with a more cautious or flexible approach, where you start with action B and then switch to C, and then maybe switch to A or D or something like, or another potential option. So the idea of the pathways map is it shows the lower regret short-term actions that you wish to take now to buy yourself more time whilst new information comes to light, whilst you can get a better idea of what your uncertainty space is that you're dealing with as time progresses. And then the sequencing of those decisions in the long term into what options you want to keep, to which options you want to keep open for the future. And then you can use a scorecard or various other methods, cost-benefit analysis, multi-criteria analysis, or what have you, to help evaluate the various pathways and decisions. So that's all I want to say about the approach for now. But what I would also like to stress is that it's not a process that you go through once. there's a phased approach. What we talk about now in Deltaris is very much this idea of a phased approach to undertaking DAP, where perhaps in the earlier stage, you need to raise awareness about what the approach is, how to implement the approach, why we might not like to implement the approach, you know, through presentations such as this, or through serious games, as we alluded to earlier, such as Sustainable Delta. Just to introduce stakeholders to the approach and the importance of planning under uncertainty and how we might achieve that. And then we move into this idea of phasing the approach and doing different levels of analysis, where we have essentially we have identified 3 levels, where the first level is more of a qualitative or narrative level, where people sit around a table. It's more of a workshop setting, and you generate narratives to scope out the problem and identify what the decision space looks like, what options are available to us, what uncertainties we need to consider, whether or not further analysis is necessary. So, do I have a problem? Help to identify any blind spots, these sorts of things, and then also to determine the requirements for further analysis and/or modeling if that is required. And from that level 1 analysis, you can move into a level 2 analysis, which is much more quantitative in nature, perhaps uses existing modeling tools or existing information, existing reports, these sorts of things, to design your initial pathways. And again, at that point, that may be enough and sufficient to move on with your planning process. You have enough information to base it upon which to base a decision. But in the instance that is not the case, or that the potential for regret is so large that further analysis is even needed, then we move into this, what we call this level 3 type analysis, where you do a full assessment of pathways. And these are the types of approaches which more agree with what Casey and Alexi were presenting earlier, where you use decision scaling or robust decision making type approaches. But essentially, in a level 3 analysis, a specific tool, a modeling tool, would need to be developed that is capable of modeling multiple scenarios, like many scenarios, thousands of scenarios, and so on and so forth, using weather generators and these sorts of things. But the levels relate to the phases of the planning process, and this is why I wanted to stress before that the DAP process itself is iterative. There are benefits in going through doing a very quick scan level 1 analysis first before moving on to something more detailed, because the idea is that we are trying to phase the analysis to help break tunnel vision and identify options that perhaps we otherwise wouldn't, and identify the situations that that may require alternative options, and open up the conversation, and to help minimize the risk of overinvestment in potentially costly and unnecessary modeling studies. In many instances, level 3 will be required, and the more complicated and the larger the issue, absolutely. But in smaller, more local issues, where you're talking at community level, then perhaps a level 2 analysis will be sufficient. The other thing is that the level of analysis can also relate to the data availability as well. In low data contexts, perhaps it may be that a level 1 or level 2 analysis is all that can be achieved. So DAP has been applied all over the world in various to varying degrees. I'm not going to talk about each of these locations, but I will focus again on America. So apologies for another American example or another American case study. But one application I do want to talk about today is a study we did for the Miami C7 Basin in Florida a couple of years ago. And I had hoped that one of our local partners there would be able to join me for this presentation and take over at this point, but unfortunately schedules did not allow. So I will do my best. So the Miami Basin, C7 Basin, it's a basin, as I say, in Florida, where the system is incredibly vulnerable to sea level rise. It's a low-lying area with a high groundwater table. The geography is dominated by sandy soils with porous limestones, and there's a very complex system of water governance there. But essentially within the area, 250,000 or so inhabitants are living there. It's mainly residential, with some commercial and light industrial activities as well. And then there is a major highway crossing the basin on the eastern side. And the reason why this basin was chosen is due to its vulnerability of flooding. So in the area, the water is managed by a three-tiered system of canals. So there's a primary system of canals and coastal structures and pumps, a secondary system of canals, and then a tertiary system consisting of stormwater drainage systems. And the key structure in the whole thing, or the boundary of the system, is what is termed this S27 coastal structure, which is essentially a large sluice, and drains the main canals to the ocean under gravity. But this system is known to underperform in relation to high sea level rise scenarios. So here we move into this idea of phasing, and initially we sat down with the stakeholders and had a session with them with maps, reports, whatever available available information there was, and looked at what were, and scoped out the constraints of the analysis, or the boundaries of the analysis. What did the system look like? What were the scenarios that we wanted to consider? What were the uncertainties we needed to consider? What options were available to us? And then an initial first run, which you can see on the screen, of how the stakeholders thought those decisions would be sequenced in time. What would be logical to do first? What would be logical to do next? Which options to combine? Which options to leave to later? So the options that were being considered were, first of all, taking no action. Second of all, local flood mitigation, which, literally flood mitigation along the property lines of individual properties, flood walls, exfiltration trenches, these types of things. Then more of a regional flood mitigation upgrade, so putting in pumps, installing pumps at the S27 structure. And finally, land use mitigation, where roads and buildings would be raised to various elevations in line with sea level rise. So then we moved into this idea of a level 2 assessment, where we take a more quantitative analysis. So here you see we've got a couple of hydrologic drivers of rainfall and storm surge to analyze. We pump them through a hydrodynamic model, which then moves into a flood impact assessment model, and that's essentially the modeling framework for this level 2 quantitative analysis. And we assess the different options that are available to us, and assess the timing of their tipping points in relation to that. And the key metric that we were using in this analysis was, first of all, how much sea level rise we could cope with, but then also the performance metric was the expected annual damages relating to those various sea levels. So, as I say, the objective was set at keeping the expected annual damages at current levels, so not to exceed them, which therefore set our threshold at that level, or the tipping point at that level. And then the scenarios, the various sea level rise scenarios, were used to determine at what point in time those thresholds would be exceeded. So we can see, for example, straight away that if we take no action, already the threshold or the tipping point is reached and we have unacceptable performance. However, under the M1 option, that buys us some time, and under M3, which was the land use measures, raising land elevation, that buys us even more time, or more change, if you will. And then in each of the different scenarios, we can work out the potential timings for those. And once we had those results of the options analysis in terms of tipping points, then we can use that information to build very simple adaptation pathways. So essentially the translation between the graph before and this figure on the screen is that the tipping points are now represented by the terminals, so you can see how much change each of the options can deal with. So for the regional flood risk management, so the upgrading of the S27 barrier, if it's a large upgrade for large pumps, that buys us around about half a foot of change, but a small upgrade will only buy, a quarter foot. Local flood risk management, again, about half a foot. So that's the translation between the modeling results and the adaptation pathways. So in generating the pathways map, you can see that we've arranged it vertically with the structural measures at the top, the land use measures at the bottom. And once we have the individual options with their individual thresholds or tipping points plotted, we can then start to build up our pathways. Once we reach a tipping point for a particular option, then we need to, that is an indication we need to switch to a new action. So what actions are available to us? What would be logical? Here, if we were to start with a small pump upgrade, then maybe we could enlarge those pumps, or maybe then we would want to switch straight away to land use measures or elevating the land. And so on and so forth. With all the different options and alternatives, we come up with the complete pathways map. Now, not every single option and every single alternative or combination or sequence is represented, but the key thing is to represent those sequences and pathways which are logical and which stakeholders support or which stakeholders prefer. And what you can take from the adaptation pathways map is, okay, so the structural measures, they are going to buy us a little bit of time. We've got a bit of time up our sleeves. We have some change. As long as sea level rise is restricted to about a foot, then those structural measures will be okay and we can cope with that. And in terms of timing, under the sea level rise scenarios, that could be, buy us 20 years to more than 40 years, which was the time horizon. But so although the structural measures will buy some time, it's more than likely that the land use measures are going to be needed in the end. Okay, so that's the other key takeaway from the pathways map. So even if the local authorities don't want to be talking about land use measures at the moment, elevating land, because that's a hugely invasive or intervention to make, like raising up buildings, raising up road infrastructure, so on and so forth. It shows that it's probably going to be likely needed in the future, but they can start having these discussions now, and when that decision needs to be made as to elevate, or if that decision still needs to be made, they can then at that point choose whether to go 6, 7 or 8 feet, because they will have more information about how the sea level rise is progressing. So that's all I want to talk about that example, and I know I've gone very much over, so I'm going to definitely skip through these slides. But in summary, what we see is that, well, we believe that DAP it's a very versatile approach to incorporate deep uncertainties into these planning processes. It's useful to help identify flexible and robust strategies. So robust strategies are those that will succeed whatever the future, however the future unfolds, and flexible strategies are those that we can switch to at various points within that time horizon. So we keep our options open for as long as possible. It uses this concept of tipping points or adaptation thresholds to determine how much change our system can cope with, and then uses scenarios to assess the potential timings of when that could occur. The pathways are then used to identify any regrets or lock-in situations that could emerge, path dependencies, and so on and so forth. And then the remainder of the process is very much geared to the adaptive nature of the plan, where we need to identify the signals to monitor, and so on and so forth. And then the last thing to stress is very much that it can be the approach can be undertaken at various levels of analysis, depending on data availability, the planning phase in which you are, and also the resources that are available to you. And I think that's another key thing to stress. So I will end it there. And if there are any questions, I look forward to answering them.
Thanks so much, Andrew. This is a wonderful presentation, and I didn't even know. I've worked in the Everglades for decades and had no idea that adaptation pathways were being used there. So we're always learning new things. One of our participants asked about you had a dot or a star in South Asia, and asked about the case study there. And Alex knew of a case study in Bangladesh. Is that the one that you might be referring to?
Yeah, it is Bangladesh. So in Bangladesh, a couple of years ago, they finished the process to develop what is being called the Bangladesh Development Plan, or BDP 2100. And within the Delta Plan, we went through the process of it's an all-encompassing integrated development plan. It's not just focused on water management, but water management features heavily in all facets of life in Bangladesh. And then within each of those facets, like for flood risk management or for drought management, in initial national level strategic pathways were developed, and we're currently in the next phase of that process with the Bangladeshi government, where we are working on how to implement that Delta Plan and regionalize those national level strategies down to more the local levels, or the regional level, where we can explore pathways at a more regional scale. So yes, it was Bangladesh.
Thank you. And there was a question raised earlier that could actually, it could apply to the early or the later part of CRIDA. And so I'll start with you, Alexi. The question was, almost every country has got some sort of environmental regulations, environmental or other regulations. And so the question is in this case adaptive DAP, as you call it, but it could be the early part of the system as well. The question is, can it be applied when you're looking for an environmental permit? That is, this is a very applied thing, right? People who are permitting usually aren't pie in the sky people. They're looking at criteria. Does this, fulfill this criterion? Can this be used for, environmental impact assessments and environmental permits and things like that? Or are you needing your people to do something differently to make this process work?
So that's a very interesting question that I actually read and I've been thinking about. And it's when you're a utility like us, you're basically one player of the big game in permitting. And we want to build a new structure, and we have to negotiate a permit with a regulator who actually has some objectives. And so from the perspective of the utility seeking a permit, we can use this approach to understand the potential vulnerability of agreeing to a permit, to certain conditions in the permit. But I'm not able to address the perspective of the regulator about how to actually set that permit. A very interesting case in the United States on the West Coast is regulating water temperature for salmonids, for the migration of salmons. We have to release water below dams at a certain temperature so that these fish can thrive throughout the year. The issue is with climate change, air temperature increases, water temperature increases. To what extent are we able to actually meet these temperature requirements in the future? And these permits are in general in perpetuity. So it's a very complex question. The method, again, can be used to definitely assess the vulnerability of agreeing to certain condition in a permit. But I haven't seen yet the regulators using these type of approaches to try to set permit conditions.
Any other responses from our speakers for that? Go ahead.
I'll briefly jump in. No, I agree with what Alexi was saying. Yeah, I certainly haven't heard of any examples where it has been used by regulators themselves. But I mean, if I'm to talk from, you know, if you like, an idealistic or theoretical idea, is that the approaches can be used to indicate what the impacts of issuing that permit, and looking at the uncertainty space, how the system will perform under a variety of different scenarios if that permit is issued. Now, if a regulator is then going to base their decision based on that analysis, they can then become aware that, well, okay, under potential futures, this is going to turn out fine, and under other futures, it may turn out very, very badly, which may mean that they need to start a discussion of putting constraints on permits that maybe they're not issued for perpetuity, as Alexi suggested. And although the current legislative or regulatory environment is such that that is what happens, but maybe it's the point at which we need to be able to adapt the regulatory system to being more adaptive, if you will. But that's just an idea and a thought.
Yeah, no, I totally agree. I'm sorry, this is Casey. That I think that, you know, regulations are, at least historically, tend to be non-flexible, right? And non-adaptive. And everything we're saying is that they should be, we in general should be flexible and adaptive. So I think there's a need there to apply those principles in that space. That's a great point.
With that, there are additional questions in the questions and answers and chat box, which I assume will be preserved in some way or another. I know our speakers tried to respond to many of the questions that were there, but I apologize if we didn't get to yours. I guess at this point I'll turn things over to Anil Mishra, if he's there waiting to summarize what's been going on in the last hour and a half.
Thank you, Will. Thank you very much. Indeed, it was an honor for UNESCO to invite speakers and also to invite all the participants to discuss around climate resilient water management approaches through this webinar. And two cases, particularly on decision scaling and adaptation pathways, were presented. Of course, we are learning lesson as we wanted to have more inclusive local case study presented. We will improve. And I would like to call for the submission of your proposal. I saw some of your question when you were asking if you have a case around the topics of climate resilient water management approach us, because we are going to continue this webinar in the coming months. We hope to have we plan a global conference next year. So please submit if you have any idea to us, and we will incorporate that. In today's presentation, which provided some of the aspect of vulnerability assessment and also the policy aspect from Deltares are very relevant. And within this framework, AGWA and UNESCO is partnering to develop a policy brief on climate resilient water management approaches that's going to be very helpful based on this discussion. Also, we have announced and will the online CRIDA course is going to start on 2nd November, not the first one. So you are invited to enroll. That UNESCO is offering that course, online training course. And we are going to take some case study from different parts of the world. And as Andrew suggests, showed from his map, we really need to bring case studies from different parts of the world and also from the local perspective in the discussion. So we will try to have those in the next series. And with that, I would like to thank our speakers, panelists, and co-organizer ICWAM, UNESCO Category 2 Center, and also AGWA. And also I would like to thank colleague UNESCO's team led by Patricia, Olivier, Claire-Marine, and those who helped to put together this webinar. So we will continue to have our webinar. We will come in a month or so time. Again, I would like to call for proposal, reach us through AGWA, through UNESCO or ICWAM. You can send your ideas and we can discuss about the upcoming series. And with that, I would like to thank all of you for today's webinar. Thank you very much.
Thanks, everyone. Thanks for coming.